I feel privileged to extend my warm welcome to all presented here to listen our guest from USA, Dr. Mary Syndonia Hubbard, who will be speaking on orogenic origins, Himalayan tectonics, and hazard and climate. Today we have 4 sessions. The first one should be introduction. I would like to introduce our Open School because the Open School is organizing this seminar. It's particularly for our guest. Now, we will have short felicitations. May I request Professor Sabina, Dean Open School, to greet our guest with flower bouquet. May I request Honorable Vice Chancellor to felicitate our honorable guest through wearing traditional handloom Jandali sash. Mary Hubbard, please.
Well, thank you very much for the kind introduction and the beautiful and colorful gifts. And thank you all for coming today. It's really special to be here. And I'm very impressed with the auditorium. And I said this yesterday because Dhaka University also had these comfortable seats, and it makes me nervous that you're all going to be fast asleep quite soon. So I hope that's not the case. So we'll try to keep this lively enough. I'll just say something about the title of my presentation. And I gather you're a broad audience. You come from many different disciplines. So the word orogeny, an orogenic belt, it's a fancy word for a mountain belt. So it's looking at the origins, where do mountain belts come from? So as I mentioned, JBT was a mathematician originally, but then kind of came into rocks from the chemistry end as well. But in addition to that, he was also a field geologist. And so my graduate school was on the East Coast of the United States in Boston, Massachusetts at MIT, and he taught down the road at Harvard. But as students, we were able to take the subway and go from MIT to Harvard, and the Harvard students could do the other. And we took classes without additional cost from the opposite university. So I took 2 classes from JBT. This is back in the dark ages, long, long ago. But he took us to southern Vermont and New Hampshire, which were several favorite places of his, where there were beautiful metamorphic rocks to look at. So it may be a little hard to see, but these little red minerals in here are garnets. So women, you may know those as it's a semi-precious gemstone. You may have some in jewelry. These probably are not so beautiful to be in jewelry. These have been caught up in shear zones in the formation of the Appalachian Mountains. In this presentation, I'm going to start with a little bit of my own background, though we heard some of it in the introduction, and I'll talk about where I'm going and what I'm doing with this lecture tour, and then we'll move into looking at mountain belts, specifically the Himalaya. But I want to talk a little bit about international collaboration. And when we get into talking about the Himalaya more specifically, we'll talk about the geology as well as climate and interactions between the two. So just in terms of where I've been, again, this was kind of stated earlier, but my undergraduate, I actually started at a small school in Vermont. Vermont's in the eastern part of the United States, but I transferred to University of Colorado, which is in the Rocky Mountains in the western part of the US. So these stars are the various places that I've been. I started graduate school at Wyoming, but my professor was offered a job at MIT and he moved there, and then I was able to follow. And that was a tremendous opportunity for me. MIT opened so many doors. My research interest is based in how our Earth's crust deforms, so how it breaks and bends and changes shape, largely due to tectonics, our plate tectonic processes. And I've worked at all crustal levels. Okay, when I teach, it doesn't matter what course, the map that's in the background, not the stars on this, but the map in the background is one of my favorite maps. And I think I show it in every class. And I show it because my work focuses on mountain belts, and it's just the color shading is reflecting the topography, the shape of the Earth's surface. So the brown areas are the areas of high relief and high elevation. And so those are the mountain belts that have attracted me. I'm actually starting right here in Bangladesh. So this is my third presentation of the lecture tour. So it's been just the last 3 days. Nepal is celebrating several different holidays at the moment. And when I get back and when the holidays pass, I'll give a couple lectures there as well. In the spring, I'll come back in March, and I'll start with Japan and give a lecture at Kyoto, and then Indonesia. I'll give several talks in various universities in India, one in Bhutan, and then ending up back in Nepal for one of the more remote campuses, as well as Kathmandu University is a private university. So why study mountain belts? The areas that expose rocks really of all different crustal levels. We've got topography in mountain belts that allows us to understand processes of erosion, some of the natural hazards, and again, some climatic themes. But probably more important than anything, people live in mountain belts, and the people in mountain belts rely on the natural resources that are there, but they're also subjected to the various hazards that exist in areas of high relief. So landslides, earthquakes, flooding, etc. And then lastly, I'll just say, as I've mentioned, that mountain belts impact our weather on a day-to-day basis, but ultimately climate as well. So why international collaboration? So this is also, I guess, one of my passions and something I think is very important. When I was trying to decide how to present this passion, I did what we all do too often. I did a Google search, and then of course I went to our university library and looked up international collaboration. Turns out that there's a whole group of researchers, and that's what they study, is what are the outcomes of people collaborating, people coming together from around the world to collaborate. So this quote is from one of those research papers. The best science comes from international collaboration. So the things that we're missing on this slide are just the dates. But in 2017, so I'm just going to give an example of the collaboration and the value of collaboration and some things that would not have happened without international collaboration. Now I'm taking you back to your secondary school or wherever you might have learned plate tectonics, because we're going to go look at mountain belts, and specifically we're going to look at the Himalaya. And the Himalaya was caused by the Indian plate, which would be represented in this cartoon on this leftmost part. Our continental crust is thicker than our oceanic crust. And so when the two come together, it's thicker and it's less dense, and so it doesn't like to go down the subduction zone. So the two continents collide, and the Earth's crust is deformed, and we get a mountain belt. So that's just your basic secondary school review on continental collision and plate tectonics. And of course, that process has resulted in this part of the world in the Himalaya. This is another slide I show when I give talks in the US. Sadly, there are a number of Americans that don't know where Nepal is when I talk about Nepal, let alone Bangladesh is behind my pointer here. But and so I show this to just show the geography, the political geography, as well as the Google Earth version, which would be the physical geography, which is what I prefer more. There's no political boundaries here, and we can really see what the Earth's crust is doing. But we see some version of this map occurs in almost every paper that us geologists write about our work on the mountain belt. And what it shows in the colors here are different bands of rock that have similar characteristics to themselves. So the gray band, these rocks have not been buried deeply in the Earth's crust. They're sedimentary rock. They're separated from the next zone of rocks to the north by a big thrust fault. So thrust faults are when one package of rocks is pushed in the collision, is pushed up and over the other one. And the rocks in here, if we could go look at those rocks, they are sedimentary rocks, but made of very coarse pieces. So when the rivers emerged, when the Himalaya was first going up, we'll look at the cartoon here, the mountains were first going up when the rivers came down and hit the flatland. They dropped that heavy load of all the coarse material. When geologists do research about the Himalaya, They ask many questions. We've already discussed some of them. When did the collision occur? How fast are those mountains going up? How much sediment has come off? And that brings us to Bangladesh, because much of that sediment has come off, gone into the Ganges River, or gone off the backside into the Brahmaputra and come around, and you end up with it here or offshore of Bangladesh. But that's an important topic these days, trying to calculate the amount of sediment and then determining where it came from and when it came from those places. On those faults, how much displacement's happened on those faults. The peak in the background on this photo on the left is called Tabache, and Cholatse is the smaller peak. And as we continue to walk up this valley and get closer to Tabache, when we get close enough to look at it, we can actually see a shear zone that cuts right down through that face. It's very well exposed. This white area is a granite over here, and we can even see some bending in the layers on the right-hand side of the shear zone, showing us that the right-hand side has moved down, apparently down, with respect to the other side. Well, my student, his name was Neil Seifert, and he continued then to work in this area for that next several months and was able to come up with a better idea of kind of what this fault zone looked like. And what he found, the purple lines on this map, well, let's just locate geographically. That village of Bengkar is right in here. Those lineaments that I showed on that earlier image were right in here. The top of Mount Everest is right up in this area. So we're just in that area. Namche is the place I mentioned earlier where the piles of dirt were that we looked at the lake beds. So just for geographic reference. I think the top part said, why are cross faults important? And so these faults that cut perpendicular to the range, we're referring to as cross faults. Why are they important? Well, in 2015, Nepal had 2 big earthquakes. And so this map, there's a scale down here, and the Kathmandu Valley is kind of this whitish area in the middle. But the other reason I think these cross faults are important, and I've touched on this already a little bit, is that the main river valleys in the Himalaya, or many of the main river valleys, they flow north-south, or from north to south, and that's where these cross faults seem to be co-located. My guess is that the rivers followed weak rocks, rocks that were broken by the faults themselves. So in terms of chickens and eggs, my guess, if I had to guess, this is only a guess, would be that you had the faulting first and the rivers that's been an easy place to erode out. But what we're left with now is that the fault rocks exist on the slopes of the river valleys, on the valley walls, and if those rocks are weakened, they're going to be much more prone to landslides. So here we see a landslide in the Malamshi Valley, and we're going to come back and look at a little bit more about the Malamshi Valley. So again, another reason I think we want to understand where these faults are. So just to back up and back out a little bit from some of the things we've talked about, we looked at that fault I was calling the Bengkar Fault up in the high mountains. Mount Everest, I think, is the peak right about more or less where the laser pointer is. And that's the zone that was originally mapped by my student. My current student, he's not current, he just graduated. I just retired. I still call him my current student. But anyway, Bibek, he mapped down to the south and was able to trace the fault down to the south. It doesn't look quite like this yellow dashed line, but we do know the fault continues southward. The Gauri Shankar lineament that I just mentioned that corresponds with the eastern edge of where those earthquake aftershocks were. And I had a master's student, Nishal Baral, who worked on some parts of that and did identify some faulting in that area. Here is that red box, is this image. The yellow is the walking path that we made. But I think you can see kind of some, again, northeast trending linear features on this image. So the goal of this walking path was to be able to cross several of those linear features. So again, this is a case where a climatic event or a weather event caused this very localized rainfall, which caused landsliding, which caused flooding in this area. Just off of this, and I'm not showing pictures today, but there's one of these cross fault zones that goes right up the Malamshi Valley. So again, we haven't done much work on that, but just have recognized that it's there. So an interplay between our faulting and our weather and our hazards. These photos are all from the 1980s. So this is 1985, and just 2 months before my first trip to Nepal, there was a glacial lake that burst through its dam. This is the Dudh Kosi River Valley that runs up to the Everest area. So Lukla would be just, I don't know, just out of this picture, probably up here. But the scarring where that flood came down and just caused lots of local landslides. So this is an example. This is a village called Langtang, and this is a before and after. But earthquakes also tend to trigger landslides. So in 2015 in Nepal, much of the tragedy that happened in the mountains outside of Kathmandu was due to landslides burying villages or causing damage rather than the shaking or even the building collapse itself. But in 2019, National Geographic sponsored this expedition that I mentioned earlier with about 40 scientists. And our geology team went up a valley that parallels the valley going up to Everest. It's called the Ngozumba, and this is the Ngozumba Glacier. And you can see a lot of melting is happening on the Ngozumba Glacier. We're standing on the moraine, and there's quite a distance between the top of the moraine ridge down to the glacier. That's all glacial melt that's happened probably in the last, since I was there in the 1980s, so the last 20 to 30 years, I suppose. So we went into that valley to actually look at some lakes, and these are modern lakes, and to actually do some coring to look at the mud that's accumulated layer by layer in the bottom of these high mountain lakes to see what signals we could pick up from the layers of mud. And we took 2 cores, actually we cored 2 lakes, I should say, and at each lake we collected 2 cores. One stayed with the Nepali students, and the other one went back to the US for analysis. And so these are 1 core from each lake. The things that we see in these cores, this one on the left actually shows that the sedimentary layers are folded. So there's been some deformation. And we've speculated about whether that deformation is recording a shaking event due to earthquakes, or whether it's just a little, like an underwater landslide, a little slumping of the sedimentary material on the steep slope underwater. So we still, that's inconclusive. The other core here on the right-hand side has very nice horizontal layering. This is the films.
Yeah, lower down slowly so we can really feel when we get on the bottom. Yeah. Yeah. And it was like all of a sudden everything came together.
Successful now, we are very happy. The mode can help us to understand the climatic fluctuation in this area.
My work with Ananta has been critical in this whole process. We've grown up seeing geology in slightly different ways. We've brought students with us, so the students have been able to benefit from the work that we do.
It was really demanding. Getting these scores out is going to help us predict what's going to happen in the future, hopefully.
First goal would be then to get incremental analyses up through the core and learn what we can about those years that we've collected. Information about water temperature, life forms that were available, CO2 content within the lake.
This is an amazingly exciting expedition. No doubt lead to many, many other studies.
Oceans are the lifeblood for 20% of the world's population. It determines whether or not there will be a successful period of agriculture. It determines whether or not there will be extreme floods and loss of life and infrastructure. The ultimate goal of this project is to turn the science into something that has value for the people.
By understanding how the climate's changing, we can help people that are in those areas make adaptations that will be sustainable for them.
Now, time to engage with the audience. And if you have any questions, and our speaker is ready to answer your question. Please.
You are exploring different elements of Earth for identifying the different problems that are causing environmental degradation. So how would you evaluate your work regarding policy advocacy? Because we know that there are so many international conventions like Kyoto Protocol or climate conventions, but there are no specific convention or international instrument regarding mountain belt or the specific problem that occurred on that region. So how would you evaluate your work in terms of addressing that point to the political leaders so that they take steps in terms of formulating an international instrument?
You know, National Geographic's goal in the work that they did with that expedition was to highlight, to bring forward actual science, actual data supporting the change that's happening there. And so that was their goal, and because National Geographic kind of prides itself in putting things out for the everyday person, so you don't have to be a scientist to watch their films or read their articles or whatnot, but to heighten awareness. And I'll say at a similar time, BBC also did a climate thing that had to do with the Himalaya, which is very good, and I don't remember what it was called, but again, the same purpose. So I think that those sorts of media outlets can be very helpful for us. But yeah, sometimes I feel like mountain people, the voices of mountain people just don't seem to get heard the same way that other places do. There have been a number of mountain conferences around the world with the idea of getting those voices heard, but yeah, sometimes it's difficult.
Do you have any idea what the nature of that crossfalls and what the reason behind this?
Those were the two of the slides I took out of this presentation, trying to shorten it up a bit, but a number of ideas have been proposed, so I'm not the only one who's been looking at cross faults. And just to sort of quickly sum up, I guess, what some of the ideas are that have been proposed. In the early 1980s, when geodesy was kind of first getting strong and people were collecting geodetic data, so looking at plate motions or the motions across faults, what they found was that if they went to the far northwest of the Himalaya, the convergence direction was perpendicular to the fault, and came down in the central part, and the convergence direction is perpendicular to the faults. Come to the east, and it's perpendicular. Well, when you put that all on this arcuate range, it's radial spreading of the upper plate in a way that's being thrust over the Indian plate. And so if you've got that radial spreading, you have to have extensions somewhere along the range. And maybe these cross faults are an expression of that extension. So that's one idea. There's a man named Laurent Gaudin. He's a Canadian, and he's been working in Western Nepal and in India, but he speculates that on the Indian subcontinent, the basement rocks, the very old rocks buried under the foreland, the land in front, the Ganges Plain and so on, there are old ridges and fault zones that trend northeast, and there's actually relief there, so you get thicker accumulation of sediment where you have almost like rift valleys, and then you have the ridges and thinner sediment over. But as that's being subducted underneath or going underneath the mountain front, could those bordering faults either reactivate a little, or just that basement topography, could that project upwards? The problem with that is that convergence vector of the motion vector of the Indian plate with respect to the Asian would have to be parallel to those ridges for those ridges to track right under those faults through time. Right now, that plate motion vector is a little bit oblique to the ridges. So then the ridges would be subducting obliquely, which still could cause faults up above. Some of the recent seismic activity on cross faults has been as deep as 50 kilometers. So that's below the main, what's called the main Himalayan thrust that people sort of see as the top of the Indian plate going down. So it's below that, which kind of supports the idea of basement structures, propagating upward. The idea that I kind of like best, but again, based on just how I feel. But if you think about Tibet, Tibet is extending east-west, and we have all these rift valleys that trend north-south. Well, it seems like those likely continue, they do continue south of the Indus-Suture zone, where the two continents came together originally, and it just, to me, it makes sense that they would continue down into the Himalaya itself, and that you're going to have that east-west extension. What drives that? That's a whole different question, I guess. And I'm not sure that's very well understood why Tibet is spreading east-west. So those are just a few ideas, but we honestly don't know the answer. And the faults themselves, I don't think they've had major displacement. I think they're like tear faults or something. The other thing, I also took a slide out that I had so I live in Montana where it's very snowy. And last winter, I was pushing the snow shovel to shovel about this much fresh snow off the deck out behind my house. And as I pushed the snow, just the consistency of the snow made thrust faults. So the snow a little layer would stack up on top of another one, and it looked like a thrust belt. But every time, a cross fault would cut right just in the width of my snow shovel, would cut across in several places the snow. So I did it again and again, and every time I pushed the snow, I got a cross fault. And that made me just think about material properties. Maybe just the strength of rocks in our crust is such that it's not strong enough to have the thrust deformation be so laterally continuous. And there's probably other asperities in there, so something hangs up a little bit and another thrust propagates, and so it's basically a tear fault in between. Now that would be restricted to the hanging wall, and the idea the fact that we have that seismicity down 50 kilometers then makes that maybe not such a great explanation. So the answer is we don't know for sure, but those are just some ideas, and as we continue to collect data, hopefully people keep all these ideas as kind of working hypotheses, and maybe we'll come up with some new ideas too.
I have one question. Internationally now, open climate campaign is going on. So in that case, so what we request to different governments and research organizations, so are working with this climate change or this kind of technological things, etc. So they are generating a lot of data. So from your research, you got a lot of findings. So are you planning to share this data to the world openly, or under what we call diamond openness? So that means sharing the data to the world openly, so that everybody can have access to this data. That will enhance the research activities in climate change and other things. So what happens about your data, so to your data? So you have generated a lot of data from your research. So all this data are openly shared, or what is your plan, and what do you think about this open platform?
That's a great question, and I think one of the things us scientists are guilty about, yes, we publish our data, so we say, oh, I published that data. Well, we publish it in journals, and a lot of the journals and the jargon, the language that we use is so technical that it's not really accessible to all. I think we're beginning to recognize that's a problem. The scientists, we live in our own little bubble sometimes, and we communicate with each other, and we don't learn to communicate beyond. As I mentioned before, I think National Geographic's idea was to come in and they have the capability to reach a really broad audience, and so that was one of their attempts. And they do have these education pages, and they're kind of targeting primary and secondary school teachers to then use some of the content again to spread knowledge. But in terms of just the data itself, I mean, it's published or is being published in journals. The trend now is for journals to be open access. That comes with its own set of challenges that we discovered in our in publishing some of this, because where in the past these fancy journal companies would charge the libraries a huge sum to cover their costs, if it's open access, then who pays? So now they charge you, the researcher. So for these articles, it's $2,500 or something to actually publish in the open access journal. And so a lot of the work, of course, is student work, and students don't have that funding. And if we don't have a grant fund, you know, that covers it, that opens up a whole nother challenge. But we have published some of this in open access journals. It doesn't help a person who doesn't know what to do with the data. I mean, that's a challenge as well. And again, that's where National Geographic's approach was more to distill it down to the basic points of information that could be understood by everybody. But I like, you know, the open resource idea is really a great concept and super important, and I think we'll see much more of that.
If we can utilize your techniques according to the change of the climate to study the change of the mud, if I understand your lecture or presentation, then I hope that it will be a great help for our Delta plan, and we can predict the future of Bangladesh. Thank you very much.
Ladies and gentlemen, allow me to extend my heartfelt thanks for your active participation in this seminar. I trust the program was both enlightening and enjoyable. I would like to acknowledge the presence of my Vice Chancellors, Pro-Vice Chancellors, Treasurer, Registrar, whose attendance and support have been instrumental in orchestrating this seminar. With the conclusion of today's seminar, I bid you all farewell. Before we part ways, I humbly request the Honorable Vice Chancellor to kindly present a university gift package to our esteemed guest speaker. Sir, please.